Chapter 1 from our textbook goes over the nature of geology. What is geology? And specific to this course, what is hydrology and what is hydrogeology? So this is just a summary of what is geology. In this course, we're going to talk about geology and we're going to relate it all back to the hydrologic cycle. And the hydrologic cycle is going to involve the surface water, the groundwater, the atmospheric water vapor, ice, oceans. We're going to stick to the nearshore environment because some of you have or will take oceanography. We're going to go around the hydrologic cycle in this course, and we'll be looking at those sinks and the fluxes, the changes from like surface water to groundwater, from surface water to the atmosphere, from plants to the atmosphere. We'll go through all the different ways that water moves around the hydrologic cycle, and then we'll put it in that geologic context. We'll talk about rocks and soil and weathering and how the water fits into that picture. So when we talk about streams, we'll talk about streams cutting through bedrock or streams moving sediment down the stream. So it'll be water, but with a geology intertwined. If we were just doing geology, it's important to understand what that geology is. It's a branch of science. So at Appalachian State University, you can take for science biology, chemistry, physics, or geology. And geology takes into account, because it's so interdisciplinary, like our majors take 2 semesters of physics, 2 of chemistry. Most of them take a biology course, and certainly mathematics into calculus. So it's very interdisciplinary because it intertwines the sciences. Geology is unique. We look at different temporal scales. And what does that mean? That word temporal means time. So time scales. Geological processes occur at different time scales. Think of like a meteorite impact. That's instantaneous. Boom. Instantaneous geologic event. An earthquake is an instantaneous geologic event. A landslide can also be like an instantaneous geologic event. Not all instantaneous geologic events cause death and destruction, but those are good examples. So those are very fast. A slow temporal scale would be something like the movement of the plates around on top of the asthenosphere, as well as sedimentation rates can be really slow. Clay falls out of the water in the ocean very, very slowly to be deposited on the seafloor. So there are different temporal scales. There's also different spatial scales. I can study the geology of one tiny little place, one tiny little thing, but I can also study the geology and geologic processes that govern the whole Earth. So we can look at little bits of time, large chunks of time, little bits of space, the whole Earth, and everywhere in between. And the Earth is our laboratory. We're so lucky. Like this image here is showing you a picture of a canyon. There is an alluvial fan, there's a stream going through it, there's rocks, there's mountains, there's valleys, there's vegetation. And in geology, we would study that whole picture, and that's our office. It's a great thing to study. If you're already thinking, I want to change my major, be in touch. Okay, so geology is the study of the processes that govern the Earth inside and out. It also looks at the history of the Earth, and so the movement of plates, volcanic eruptions, evolution of organisms over time. Sorry, I kicked my table. And so there's many different goals when you look at the different facets of geology. One of those goals when studying geology is to think of that interaction between humans and the Earth. And so in hydrology, or in this water class, we really need to think about our effect on the hydrologic cycle and our effect on Earth processes. So a lot of what we talk about will be surface processes, and we'll intertwine maybe some case studies of pollution and climate change and erosion and how humans change the hydrologic cycle as we go along. Okay, so hydrology, that's just the study of water. A lot of different people could be hydrologists. They don't have to be hydrogeologists. In this course, we're going to do water, but take a step further and do the geology part along with it. So a geologic field dealing with the interrelationship of geologic materials, rocks, and sand, and the processes that happen in the water cycle. All right, so water and geology influence where we live. I'm going to move my face. The image here with the house is a house on stilts. People love living near water. I like to live near water. We go to lakes and rivers and the ocean, waterfalls for vacation. So here's a home. They want to live on the water. This looks like the Mississippi floodplain. And by the nature of living on a river system like that, you've got to have your house on stilts. There are a lot of houses in the Watauga River floodplain here around Watauga County, as well as the New River floodplain here and into Ashe County, where the houses are on stilts. So drive around and take a look at those, and that's because the house is in the floodplain. We also like mountains, so living near a volcano, right? It's a beautiful, majestic landscape. It's also hazardous, not just lava flows, but also with ash that comes off of a volcano. So living near these beautiful mountains can have its benefits because it's beautiful and they're rich, organic, agricultural soils, but also there can be hazards. Okay. Here's one of my kids. That's Bodie standing on a cliff and just showing like we love living in the mountains. There are hazards that are associated with us living in the mountains here. Some of that has to do with landslide activity. So I was going to say we're not near a plate boundary, so we don't have volcanoes and earthquakes. But if we had a one the other day in North Carolina. Yeah, so we live in the mountains. We want to live here because the geology is cool. We think it's the cool mountains, but it's these beautiful mountains are here because of geology. Okay. Geology governs resources. So here is a map of most of the United States and Canada. And on this map, what is highlighted are rocks of the Canadian Shield and rocks of Western North America. And they're very different. In the Canadian Shield, the resources are different. There are iron mines. So iron has accumulated and we can go there and extract it. There's enough there that it's profitable to get it. In Western North America, there are copper mines. In these copper mines, there are coppers found as veins, and there's enough of it that it's economically viable to get that copper. So there's copper in Western North America, and there are iron mines in the Canadian Shield. Well, aren't there some of each in other places? Well, there's a little bit of iron in Western North America, but most of it's in the Canadian Shield. Why? Well, those rocks are billions of years old, 2 billion years old. And the iron was deposited at the time our atmosphere was accumulating oxygen. And so the accumulations of iron there are iron oxides. During that early atmosphere, plants are creating oxygen and fixing that iron in place. So the billion-year-old rocks of Canadian Shield have iron in them, whereas Western North America, those rocks are younger. Those are more in the 50 to 150, 175 million years old. And at that time, the mountains of Western North America, notice there's lumpy topography there, it's very mountainous. There was high heat flow, hydrothermal activity, and copper was deposited in veins around magma underground. Okay, so geology, the age of the rocks, the nature of what's happening during that time can give us different resources. Okay, so a geologist sees the world in different ways. So I'm looking at this picture. This is in the Theodore Roosevelt National Park in North Dakota, and there is a muddy river flowing through some cliffy sandstones. In this image, I think of the geologic history in two ways. There is a past geologic history that are those sandstone cliffs. Those are old, those are a couple million years old. Then there is the recent geology that is the stream cutting through the cliff and the deposition of the point bar. This is the point bar right here, and that is where the water is slow as it goes around this meander, and the slow velocity of the water creates a depositional environment that is a point bar. On the inside that bend, the water's faster, and we have that cliff erosion. So there's kind of two different pulses of geologic history here. The formation of the sand deposit that became those cliffs over time, and then the recent geology that is that river cutting through the landscape and depositing that point bar. Okay, so that's how we're going to look at landscapes. What's the geologic history? What can the landscape tell us? Here's another one. So here is a lake at Glacier National Park in Montana. In the background are some mountains with ice in them. Some of it's glacial. And then the foreground, there's a big lake. So there is two parts to the geologic history here. Part of it we can't see. So this is a typical landscape in an area that's been glaciated in the past. So it's Glacier National Park. Part of that is because there's glaciers there, and part of it is because there's a rich glacial history. So this is a U-shaped valley right here up to a peak, and then another U-shaped valley. And over here is an arête, and those landforms, U-shaped valleys, cirques up in the mountains, and these arêtes tell me that this whole landscape was full of glaciers at one time. The whole area was full of glaciers, and now the glaciers have receded. That's okay, just up into the mountains. And then the new landscape is this landscape with smaller pocket glaciers, and then this outwash of the water here making the lake. So two parts to that glacial history. Ice on the earth, here's 28 BPs before present. So 28,000 years before present, and here is present. Let's look at today. Today we have ice on Greenland. There's a large Greenland ice sheet, and then ice in the Arctic Ocean. On the left, notice that Northern Europe, Russia, Canada, and into Northern United States, we had ice at 28,000 years before present. The ice had been melting for the last 15 or 20,000 years to give us what we have today in the present day ice situation. Why is it melting? Because the earth heated up. So the earth has been warming since 15,000 years ago, and now we have the present situation with our ice accumulation. That's a part of the geologic history of deep time climate change. At the end of the semester, we'll talk about anthropogenic climate change and what's happening now in the present with those ice sheets and the sea ice. All right, what's inside the earth? We're going to spend some time here in the early days of the semester talking about rocks and plate tectonics. So in order to do that, we need to know what happens when we go down into the earth. I'll move my face. So we'll start the inside. On the inside is the inner core. It is made of iron and nickel, and that formed during what's called differentiation in the early history of the earth. Planetesimals bombarded, and the whole earth melted, When it melted, the iron and the nickel sunk down to become the core. The outer core is liquid. It's liquid because it's so hot. So the inner core is solid because of the high pressure. The outer core is liquid because of the heat that balances out. And it's still iron and nickel, the outer core. The mantle goes from the outer core to the base of the crust and can be split into two, the lower mantle and the upper mantle. And the mantle is iron and magnesium rich. The name of the mineral here is olivine. Olivine is an iron and magnesium rich silicate mineral. It's green. The gemstone is peridot. If you, I think, July birthstone. So that has a lot of iron and magnesium, not as dense as the nickels and the iron of the core. Okay, and then the crust is that outer thin layer, 20 to 25 miles thick, maybe a little deeper underneath mountains, and then the oceanic crust is just 4 miles thick. So we have two different kinds of crust, oceanic and continental. Oceanic crust is all made out of the rock type basalt. Continental crust, the term here, it says granitic. That would be if you were to take all the continental rocks and crush them up and melt them and recrystallize them, it would come out average as a granite. So granite's kind of average of the continental crust chemical composition. Okay, so we're going to go through those layers again when we talk about plate tectonics, but that's just the beginning of that. There are, let me move that, different forces that act on the earth, and those forces are going to change the earth and create the earth processes. So let's start here with electromagnetic energy. That's the sun energy. That's going to heat the earth from the outside. When you heat the earth from the outside, that gives us differential heating because the earth is tilted. We have our seasons, and differential heating gives us wind because it changes the high pressures and the low pressures. So we have wind. It also heats the oceans. So we have hot parts of the ocean and cold parts of the ocean and denser and less dense parts of the ocean, which gives us our ocean currents, which moves heat and cold around our earth with these big ocean currents. We have gravity. Gravity's good. Gravity makes water flow downhill, sediments go downhill, ice from our glaciers flows downhill. So we have gravity. Gravity also gives us tides. So tides because of gravity. There are hydrostatic forces. These are forces within the earth that are going to be kind of equal on all sides and push at rocks. Radioactive decay is a constant source of heat inside the earth. So when atoms form, they can be isotopes, and those isotopes can be not stable. And when they're not stable, they fall apart, and that is they decay, and that's radioactive decay of unstable isotopes. There are, of course, stable isotopes, like oxygen has different isotopes. So we have stable and unstable. The unstable ones inside the earth give us some heat inside the earth. Okay. There's also leftover heat. I think that's what they're trying to show here. This leftover heat from the formation of the earth, all those planetesimals hitting and coming in to form the earth in the early stages of the formation of the earth, and some of that heat is still left over. We have air pressure, so there's pressure of the air on the earth. Okay, forces. So because of the heat and the exchange that happens with that heat, we have plate tectonics. And plate tectonics is going to be a whole chapter, but it is the movement of the outside of the Earth, we're going to call the lithosphere. It's made up of the crust of and the upper mantle. That's going to move around on the Earth's surface on top of the asthenosphere. So here's a beach in Oregon, Ecola State Park, and the topography at that beach occurs because that beach is at a plate boundary between the Juan de Fuca plate and the North American plate, and there's a subduction zone there where North America is holding steady, but that Juan de Fuca plate, let me try to move my hands here, is subducting underneath, Juan de Fuca is subducting underneath North America here, popping up the topography at the coastline in Oregon. We're going to talk more about plate tectonics all semester. Some of another effect of that subduction zone is volcanism. So here's a smattering of some of the Cascade volcanoes in the Pacific Northwest. In the foreground is Mount Hood. The background's St. Helens, Mount Rainier, and Mount Adams. So those volcanoes are there as a direct result of that subduction zone. Here we are in the Blue Ridge Mountains of North Carolina, and home. The mountains here are a result of tectonic collision. So if that subduction zone was to continue, and there was my elbow was another continent, they would ram into each other. So two continents rammed into each other to form the fold and the thrust mountains of the Blue Ridge Mountains. We're going to talk more about that in plate tectonics, but there's these mountains have eroded after the formation of the Appalachian Mountains. Okay. Solar energy. So we have ultraviolet energy that's coming from the sun. Some of that is blocked by the atmosphere that heats up the earth and causes precipitation because of evaporation from the Earth's surface. We have clouds, they get heavy with water, and then we have precipitation that fills up our watersheds, and we have flowing rivers. Here's evaporation down here from the ocean. And then that differential heating, because the tilt of the Earth and clouds gives us high and low pressure systems on the Earth, and the wind blows from high pressure to low pressure. So we have the movement of sand and dust around the Earth and clouds. All right, so here is Sleeping Bear Dunes National Lakeshore. This is along the Great Lakes in Michigan, and it's heating up this water. The water's evaporating and making these beautiful clouds. We're going to have a chapter on rocks, but this early chapter in your book talks about different places where we can expect rocks to form. And we have three rock types. We have sedimentary rocks that form from pre-existing fragments of rocks, or from precipitating out of water like a limestone. We have metamorphic rocks that form in heat and pressure changes, and then we have igneous rocks that form when magma cools and crystallizes, when we take liquid rock and we crystallize it into a rock. So this section is about different sediments and what we might expect to find in different places. So there are certain sediments that form in glacial areas, sediments that form in rivers, different sediments in lakes, mountains, deltas, shallow water, deep water, and sand dunes and beaches. In a glacial environment, we're going to have coarse-grained sediment, gravels and whatnot, and the same thing in mountains like boulders and gravels. Whereas a river is going to move those sediments downstream, and some of that may get deposited in lakes. Lakes are going to have a smaller grain size, and then out to a delta, there's going to be sedimentation at the mouth of the river. Sand dunes are going to be areas where the sediment, mostly sand size, is moved by wind, and then beaches are going to have currents that deposit sand. In shallow water, then there can be sand deposits. In deep water, where the water's not moving as quickly, then that would be where we would find like muddy environments and maybe also limestone or coral reef deposits. So here's a beach that has coarse grained pebbles on it. They're rounded because of the wave action. Here is a delta that is forming where one creek is coming into another at Glacier National Park. So these are sediments that are forming as one body of water enters another. That river enters, the Avalanche Creek enters into the main river at Glacier National Park. Here's Lake of the Clouds, Porcupine Mountain State Park, and a beautiful lake. And in a lake environment, this is where we're going to find muddy bottom, so the squishy, muddy bottom of the lake. Here is sand dunes. So we find sand dunes in different environments. On the left are the dunes that are in Death Valley, and those are going to move back and forth across the floor of Death Valley. On the right, that's the sand dunes of Jockey Ridge of the Outer Banks of North Carolina. These are derived from the beaches and the movement of sand because of wind on our coastlines versus dunes that are formed in these mountainous areas out west. Here is the New River as it flows through Todd and Watauga County, and there are coarse-grained sediments, but there's also muddy sections of the New River and lots of bedrock. Here is bedrock. This is the Watauga Gorge on the Watauga River towards Bethel in North Carolina, so in Watauga County. Lots of big rocks. Glaciers create fine-grained sediment. We call that glacial flour. So these glaciers look dirty because they've crushed up rocks and they're old, and so old crushed up rocks are within that glacial sediment. All right. The other rock type I mentioned was metamorphic rocks. So metamorphic rocks are going to form within mountains where there's heat and pressure, and that heat and pressure is going to change mineralogies and change textures and create a new rock type. We also have volcanic rocks. So volcanic rocks can be intrusive and extrusive. If they're intrusive, it means they formed inside the ground and they intruded into the country rock or the rock that was already there. This is Devil's Tower. This is a old volcanic neck. So it's like the interior plumbing of an old volcano. Extrusive igneous rocks are those that are going to fly out of the volcano. So they extrude out of the volcano. They erupt out of the volcano, and here is a large field of rhyolite in this canyon from Yellowstone National Park. All right. We have a whole chapter on rocks. Here's the rock cycle, though. We start with that magma. How does magma form? It's going to form through melting. Maybe that melting is melting metamorphic rock or melting an igneous rock. The metamorphic rock is going to form by heat and pressure. The pre-existing rock can be either an igneous rock or a sedimentary rock. Metamorphic rocks are going to erode and break down through weathering and erosion and form more sediments. Sedimentary rocks can break down through weathering and erosion and form sediments. Sediments can be compacted and cemented and become sedimentary rocks. I think the only thing I didn't do is igneous rocks can weather and erode and become sediments. If you take an igneous rock and you melt it, it becomes magma. So the cycle continues. And we'll talk about each of the individual rock types in the rock chapter. All right, the Earth's surface. So the point of this course is to understand the water interaction with the Earth's surface. So here's part of the not all of, it's definitely not complete, the water cycle. There's precipitation. That precipitation is going to infiltrate to become groundwater. That groundwater is going to flow and eventually maybe make it down to the ocean. Streams are going to flow. They form in watersheds. That stream is going to flow down and maybe eventually make it down to the ocean. The ocean then is big surface. There's evaporation all over the surface of the ocean, and that water goes back up into the atmosphere to be precipitated again. Precipitated again. Precipitation, become precipitation. Water's moved around in our ocean basins through ocean currents because of wind or density differences between different bodies of water. So we are going to investigate all of this, all the different processes in this course. When you're thinking about water, we think about the movement of it between these reservoirs like the ocean or the glaciers. We also think of it as moving through different spheres. So the atmosphere has clouds that are full of water. The hydrosphere, in this case, would mostly be the surface water. And then in the lithosphere, we have more water. Our groundwater is there. The biosphere is full of water. So 71% of the Earth's surface is covered with water, and everywhere on the surface of the Earth, that 71%, that water is actively sublimating or off of glaciers or evaporating off of surface water to form the vapor in our atmosphere.